Okay, I'd like to welcome everyone back to the first colloquium this term. To kick off this seminar series, we're very happy to welcome Professor Priyamvada Natarajan. Priya is a professor at Yale and the current chair of the astronomy department. She's most well known for her work on gravitational lensing, particularly as a probe of the nature of dark matter and dark energy. She's also very well known for her work on supermassive black holes and understanding their growth and evolution, which is very related to what she'll tell us about today. Priya's work has been recognized through many awards and honors. To keep this brief, I'll just mention perhaps one of the most recent, which was being elected a Fellow of the American Academy of Arts and Sciences. We're very fortunate to have her here today, so without further ado, please take it away.
Thank you, Gabby, and everyone for that kind introduction and invitation. It's my first time giving the Princeton Colloquium, so I'm particularly delighted. I've been to the IAS before, have very fond memories, and in particular, have a real fond memory from the visit 15 years ago when John Bacall was around, and I remember many fun conversations with him, with Jim Peebles, with Scott, and thank you so much, all of you, for coming. In particular, Netta, I see all old friends here. Thank you for your encouragement over the years as well. Anyway, today I want to talk a little bit about the new insights that we are gaining into the formation of supermassive black holes, in particular from the highest redshift black holes that have been detected by the James Webb Space Telescope. But before I start, I just wanted to give a shout out to a lot of people who over the last decade or so have been working on various channels trying to understand the formation of the first black holes. And one particular reason, other than the fact that I, of course, find all of this work super interesting and exciting, is that, you know, for about a decade, we were kind of in the woods. People were not interested in trying to understand if there was any other channel to form the first black holes other than the population 3 stars and their remnants. Never mind that we have yet to detect an actual population 3 star. So it's not that other seeding mechanisms are well established. So there's a gang of us who've been working on trying to see if there could be multiple other channels in addition to the formation of the first seed black holes from population 3 remnants. So, and I am happy to say that our time has come with JWST. Let me see if I can advance my slides.
Click on the screen.
I see. Yeah, you're right. The cursor was not on the screen. Okay, so here is a brief overview of my talk. So I want to alert you, if you haven't already been alerted the last couple of years, that we have a real revolution in our understanding of supermassive black holes. And this is mirroring, coming on the back of the revolution that we have seen since LIGO first detected gravitational waves from merging stellar mass black holes. So I think the more massive cousins are mounting a revolt, and we are now starting to understand quite dramatically what's going on with black holes, both as populations spread over cosmic time, as well as the earlier sources. And then I want to talk a little bit about the various formation channels. As I mentioned, in particular, I want to show you that there's now new interesting evidence showing that there can be, and most likely, more than one channel to make the first black holes. Then I'll talk a little bit about how the evolving census of the highest redshift population of black holes. In particular, I'll focus on 3 black holes that have been detected at redshift greater than 10 by James Webb, and how, you know, contrary to our usual understanding in astrophysics, where not a lot can really be learned from a single source, I want to make the case here and hopefully convince you that these 3 black holes are transforming our understanding of the formation of seeds. Then I'll talk a little bit about challenges to constraining seeding from observational data, because as you can imagine, the closer we can reach the epoch of seeding, the tighter actual constraints we actually have on those scenarios. Then I'll close with some exciting new future prospects. So what has been really incredible is that James Webb has opened the redshift greater than 10 window. And accreting sources have been found in many, many surveys, uncovered jade, Sears. This is not even a full list. There are many, many more acronyms that could be there. A lot of time has been devoted to uncovering the highest redshift sources, both galaxies and the black holes that they may host. So interestingly, these three sources, which I think are going to have taught us a lot, even in the last year or so, at redshifts greater than 10, like a mere 400-ish, few 400-ish million years after the Big Bang. They are in place. They are supermassive already. And so, and I want to also show that we have leveraged the power. Actually, it turns out, not just JWST and Chandra, but also Hubble, incidentally, because of the fact that the Hubble frontier fields mapped out these clusters. These clusters are nature's magnifying lenses that have actually brought these sources into view for us. So we are starting, I think what is really exciting to me is that we're starting to image quasars now and their host galaxies at redshifts 7 and beyond. And I think this is going to get pushed. Some very nice results from several groups that I urge you to look at. And of course, as you all know, last year there was an amazing announcement, long awaited, of the detection of the integrated gravitational stochastic gravitational wave background emitted from merging binary supermassive black holes over cosmic time, reported by the pulsar timing arrays around the world. And I was very fortunate to be involved with NANOGrav. And what was reported is evidence for the existence of the stochastic background, which looks like that, consistent with the Hellingsdown's prediction of what it should look like. And I think, watch this space. There were many independent pulsar timing arrays that reported detection at roughly the same significance level. And now efforts are on to combine the data, because not all of them, some experiments are in the southern sky, some of them, they don't include the same pulsars. There are, of course, a few common pulsars, but they are largely independent in terms of even their analysis methods and so on. So I think we have now seen this is collective emission, collective astrophysical activity by supermassive black hole populations. And this tells you a lot about our understanding of how populations grow and evolve over time. So now let me move on to telling you a little bit more about the formation of the first black holes and the observational tests of these seeding mechanisms. So as you all have probably heard for a very long time, this is the traditional lore that we have the first generation of stars, which are preferentially more massive, that form very early in the universe. Of course, their mass function is still highly uncertain, but we believe that they will be tilted high, and therefore their remnants are likely to be massive. And these remnants could be somewhere between tens to, say, a few hundred solar masses. This is highly uncertain, but these remnants are a very, very robust prediction for the formation light seed black holes in early halos, atomic cooling halos at extremely high redshifts, from which, environments in which they can then grow vigorously or not, depending on the particulars of where they are. It turns out that recent simulations of the formation of the first stars, as I'll show a little bit later, find that these early black holes that form in a cluster, because you form a cluster of population 3 stars actually inhibit each other's growth, and they do not grow that dramatically. So it's looking a little tricky to find. Of course, there will be environments that are conducive to growth, but it doesn't look like automatically the environments where they are born are going to be conducive to rapid growth of these light seeds. So it's a kind of an interesting challenge. And those of you like me who've been in the field now for about 20 years, I remember when I was in grad school, we were talking about the formation of the first star. So there was only one star, right? It was believed that you make one star in any astrophysical setting. Once simulation resolutions improved, we realized that you form a clutch of first stars. It's a population that you actually form. So I think a lot of progress is needed here. And JWST is already showing us galaxies that are well in place with good sort of robust stellar populations, 12 to 14, suggesting that the first episode of when stars form is actually getting pushed back into higher and higher redshift. So the other channels that many of us have been working on for the last 10, 15 years are these alternative ways to, and therefore alternative environments. So, and we club them as heavy seeds is just to distinguish them from the population 3 remnant. So they could range in mass anywhere from about 10 to the 3 to 10 to the 5 solar masses. And so one route is a nuclear star cluster where you form a cluster of stars, and these will actually end up producing black holes that will merge. There are multiple dynamical mechanisms that people have proposed. I'm not going to go into those details for our purposes. It's just that the nuclear star cluster offers a nice incubator and environment, gas-rich early nuclear star cluster, where you can form a seed that ranges in mass from about 10 to the 3 to 10 to the 4. Then there's a class of models that have been suggested by many of us where you could actually, under certain circumstances, conditions that are available, rare but not exceedingly rare, available in the cold dark matter paradigm, where you could form direct collapse black hole seeds. And so they require a set of conditions, and it turns out that these conditions are available cosmologically. So these are basically proto-galaxies where you avoid fragmentation, and so you delay star formation per se. You form a pre-galactic disk that is massive, that goes unstable, and can then give you a direct collapse black hole. So once again, the conditions that are needed is you require metal-free gas, and you want to prevent, the reason for that is you want to actually prevent cooling, fragmentation, star formation. You want to bypass that somehow in order to effect direct collapse. And we find that these environments are available, and there are many models now, many different pathways to effect direct collapse. And all these scenarios that have been proposed and have been investigated give you a population of more massive seeds, and each of them works and is efficient at various epochs. So let me go through a couple of those scenarios that have been proposed. And this has been proposed by Jared Johnson, Mohammed Latif, John Wise, John Reagan, and others. And this is from a computational perspective where they have looked at the evolution of the formation of direct collapse seeds from the very, very turbulent cold flows that you have at high redshift. And these have been found in the adaptive mesh refinement code ENSO. And they start seeing sort of onset of collapse. Of course, as you all know, there is no code that actually forms a black hole, right? So you're en route, you're inevitably going to collapse is sort of where everyone's at. So you form a very compact core, turbulent cores in this case, and you will eventually form seed black holes. And so what they find is you form a structure that could be mapped onto a supermassive star. So it can be quite massive, and that is expected to evolve and give you a 10 to the 3 to 10 to the 4 solar mass black hole. And that scenario is meant to work at redshifts of about 20 or so. So then there's a scenario that we proposed, and this is not yet seen as such to progress within a simulation. As I told you, simulations are not there yet. But once again, the conditions that we require and the particular configuration that we require is found cosmologically in lambda CDM. So this is a very particular setting. Okay, so I think what's interesting about this is that it's a very particular setting which allows you to go all the way through to the formation process to link to observables, to actually make the full kind of circle. So here, what you have is this scenario sort of works. We believe we have the conditions lambda CDM between retro 15 or 20. And what you have is a main galaxy that has formed population 3 stars, and it has satellites as galaxies are 1, 2 in CTM. And the Lyman-Werner radiation from the galaxy, the parent galaxy, irradiates the subhalo, which has pristine atomic, it's a pristine atomic pooling halo. And these Lyman-Werner photons dissociate any molecular hydrogen that may form, and therefore you do not cool rapidly and fragment here. Instead, you assemble this pre-galactic disk that can go unstable and then give you a direct collapse black hole. Oh, because they are locked in as parent and satellite, this DCBH that forms in this subhalo will rapidly merge with the parent galaxy. And it turns out that this merged object, which we rather unimaginatively called overmassive black hole galaxies, have very specific and interesting observational signatures. So this would be a transient object where for a period of time, which we predicted to be roughly a redshift of 9 to 12, you would form an object whose spectrum would be dominated by accretion onto the black hole, where the black hole mass would be comparable to, and in some rare instances, maybe even exceed the mass of the stars. The stellar population is entirely acquired from the parent galaxy. And so what we were able to do in the STOI model was actually predict the co-evolving spectrum of this object going forward when the black hole is actively accreting and you have a stellar population that is in place and that is aging. And what we found is that there are very clear-cut spectral signatures. And of course, fortunately, these signatures were detectable by JWST. So we wrote a paper in 2017 detailing in this sort of model all the way from the formation of the seeds to how we could actually test using upcoming JWST data. So one of the key properties of these overmassive black hole galaxies is that they would be X-ray bright. But of course, X-rays at these epochs would be re-radiated and moved into the infrared. So you should see an elevated, conveniently for us, for JWST, elevated infrared flux. So this object will have to be detected in the X-ray. That's what sets this scenario apart, right? And you can compare and contrast the one of the joys of building somewhat idealized models is then you can actually further test them. And one test we looked at is to have a similar early galaxy, which has a POP3 forming seed, and then its growth and evolution. And we can compare the growth of the black hole in these two settings and the spectral signatures and the evolution. So this is something that we were trying to do from 2015. And in 2017, we were actually able to make some concrete predictions, which I'll come to next. Meanwhile, there's yet another setting, which is a riff on the setting that we proposed. And this was proposed by Kirk Barrow and John Wise. And they sort of they opened up the situation and said, well, what if you are not locked as a parent and a satellite, but you are just a halo in the vicinity, a nearby halo in the vicinity of a halo that has formed POP3 stars? So you have would be an early starburst, and you still have the Lyman-Werner radiation. So you have an atomic cooling halo. You do still form the direct collapse black hole. But now what you could end up having is that you have one of these stars that has been acquired in this subhalo or nearby halo actually go supernova and evacuate and expel all the other stars in it, and you end up with a giant H2 region in which you have a DCBH that's embedded. So this is another scenario where, and the reason this is also an interesting one is because you can actually predict in color space how this thing would evolve. And you can predict the detectability, and the flux. And what you see is in this case, because these are rapid dynamical processes, relatively speaking, you can make a track for such a black hole. And it turns out that these tracks mean that it will actually be visible. So I want you to see the inset here. This is the predicted AV magnitude in 2 microns. And you can see that we would be hovering within detectability of JWST for brief periods of time. So unlike that other scenario where I showed you that that transient object would live for a reasonable amount of time from, say, redshift 9 to 12, here you have another setting for the formation of direct collapse black holes, concrete signature yet to be detected. So we don't yet have a detection. People are looking. Yeah, Elliot, did you have a question?
Maybe explain a little more. How do you predict the accretion rate on black holes when they form?
Yeah, I'll come to that. Yeah. Yeah, very simple. It's a very simple model. It's just a 1D hydrodynamical code where we do the radiative transfer post-processing, but we allow for super Eddington accretion. It's not Eddington limited. So it's a very simple kind of prescription. Actually, I think I probably have a slide that's coming up a little later. So another setting, which I think is also super exciting, is a scenario, a formation scenario for direct collapse that can happen in the universe much later at redshifts of about 8 or so, and doesn't require all these sort of pristine gas that we required for those other scenarios. And this is work done by Lucio Meyer's group in Zurich and my former graduate student, Pedro Capello, who is working there. And this is a setting where basically you have 2 fully formed massive galaxies that are gas-rich, may or may not themselves be seeded prior with black holes, and they merge. And during this merger, a dramatic violent merger, you could form a very, very nuclear, supermassive disk from gas with very high inflow rates. And once again, this is not something you can follow all the way down to the core, down to the formation of the DCBH. But they noticed that this nuclear supermassive disk contracts and will inevitably likely collapse into a black hole. So this again could give you masses of 10 to the 4 to 10 to the 6 from the get-go. So, but this is at redshift 8-ish. So this is when, remember, well, you need a couple of other things in place. You need to have a lot of massive galaxies in place. You need to have them merging. And so this is where we are in terms of our ab initio formation of black hole seeds via multiple channels. So I think the point I want to press is that the astrophysics allows you to have multiple feasible channels in lambda CDM. Of course, the relative efficiency of these and which of these actually occur and whether there are further restrictions, we do not know. So at this point, what we can do is really produce concrete observational signatures, even if it's a little bit hand-wavy and simplistic, to see if we can actually ratify that these multiple processes actually occur. And I just want to make a note here that, the seeding implementation, so there are all these fantastic cosmological simulations now that follow the formation of galaxies and their supermassive black holes over cosmic time. And seeding there is done in many different ways. So in a lot of, it's pretty ad hoc overall, right? So nobody, once again, is forming ab initio, and they are not implementing in detail any of these scenarios yet in those simulations, right? And there are a bunch of different ones. One that is interesting that stands out for me that is a recent one run from the Carnegie Mellon group, Tiziana Di Matteo and her collaborators, called the Astrid simulation. And this is a simulation in which I told you, it's an ad hoc, prescriptions are added in at some level. So they use the initial mass function that we predicted from direct collapse, and they allow these black hole seeds to form throughout cosmic time. So wherever you have a pocket of gas that satisfies those conditions, you end up being able to form a direct collapse black hole. So that's what sets this simulation apart from some of the others. So I just want to let you know that what is really adopted in these simulations are recipes, right? So there are many groups, and they've been trying out. It's fantastic. There's been a lot of activity in terms of different fueling modes, feedback prescriptions, star formation prescriptions, as well as black hole seeding. And as you can imagine, part of the challenge with black hole seeding per se is that by the time you see a black hole population, observationally you detect quasars, you have had seeding convolved with the messy accretion and merging processes that grow the black holes over time, and the dynamics, especially during the mergers, that are really highly uncertain, right? So there is, I'm particularly fond of this paper, especially because, it was a wonderful collaboration with Tal, who left us too soon. So this is a setting, another setting in which you can form direct collapse black holes, or more, sorry, not quite direct collapse, but massive initial seeds. And this is a setting in an early nuclear star cluster. So this is delving into one of the scenarios. There are many other scenarios involving nuclear star clusters. I'm showing this because this is one that I'm particularly fond of for other reasons, as I mentioned. So you have a black hole that has formed from one of the stars. It essentially is scattering of the stars and growing sort of by wind-fed accretion, and settles down as it gets really massive centrally. And so you can then track to see roughly how much mass it would gain. And of course, that depends on how gas-rich the nuclear star cluster is. So we were able to show that these nuclear star clusters can behave like incubators for black hole seed growth and give you a seed, once again, of 10 to the 4, 10 to the 5 solar masses. And what's interesting is that they could produce sort of off-center accreting supermassive black holes. Another interesting thing about this setting, I keep referring to nuclear star clusters as closed boxes, is the fact that you see nuclear star clusters at various epochs, not just at the earliest epochs, even at late times. And what the gas content will, and of course the feedback physics in detail, will determine the end state. So nuclear star clusters could give you seeds on a range of masses over a range of cosmic time. So, I realized that this particular scenario could give you continual seed formation over cosmic time, down to redshifts of 3 even, right? So that's very interesting. And this was another paper that we wrote like a few years ago before JWST was launched. And I think that one of the arguments that has been made is that JWST is turning up many more galaxies, many more black holes than we ever thought existed, and so on. And I think I just want to say that I've spent time on these multiple scenarios, because if really we are able to seed black holes in multiple different channels, then it's not surprising that we're seeing many more of them, because previously we believed there was only one way to make it. So in terms of the observational signatures for all these models, starting from seeding, you can make some simple semi-analytic estimates of how the population itself will evolve. And these are sort of semi-empirical models that have been developed over the past 6, 7 years that successfully look at seeding. So I think I want you to just notice, the details are irrelevant, just want you to notice that light seeds, this is the population of light seeds that has been evolved with some accretion prescription and mergers, including mergers out to late times. This is the X-ray luminosity function of the light seeds versus the heavy seeds. The heavy seeds are in cool colors, the light seeds are in warm colors. I mean, just as you can see, these are models that are calibrated with the population that we know exists as luminosity function of redshift 6 quasars. It, of course, satisfies many other constraints at other redshifts as well. But these are the high redshift predictions where you start seeing the signatures of seeding emerge, unsurprisingly, right? As you get closer to the seeding epoch, you are likely to be able to discriminate and deconvolve the effects of seeding from dynamics and messy astrophysics in terms of accretion and mergers. So here you see that, at redshifts of 12 or so, if you had an instrument like AXIS that is able to detect sources, you start seeing real differences in the luminosity functions. They start to emerge a little earlier, but they're going to be much more observationally challenging to disentangle. And of course, the key discriminant for heavy propagating models with starting with light seeds or heavy seeds is going to be gravitational wave signatures for LISA. So here once again are a set of predictions. As I told you, there are many uncertainties. One of the fundamental uncertainties the community is grappling with right now is the efficiency of mergers, of how often do halo mergers lead to galaxy mergers, lead to black hole mergers, and the timing, the time lag in all of that. That's not well understood, right? And there's a lot of work that's ongoing because it's very critical for the LISA mission, right? That's really what we are after in terms of the number of sources. So people are building models. We have one in the mix. And so in this one, the left-hand side is pessimistic. Like, there's a probability of finally the black holes merging is only 10%. And then this is the very optimistic one where almost every black hole is going to merge within a Hubble time. And then you get these predictions for the event rate expected for LISA after 4 years. So this is as a function of redshift in the upper panels and as a function of chirp mass in the lower panel. So once again, you can just see the warm colors and the cool colors are representing heavy seeds that you can start discriminating between scenarios. And you can see, you might say, why is this tilted to low mass seeds? It turns out that light seeds are more ubiquitous, and you need, as you know, you now need a lot of conditions. So these are going to be rarer in number. So this is just the sheer, reflecting the sheer number overall of the more abundant light seeds that you have in the universe. So strangely, despite all the confounding processes that I've been alluding to, it turns out that the occupation fraction of black holes in low mass galaxies at low redshift may actually give you a clue to seeding as well. So as you know, this is very nice work that has been led here by Jenny Green and her research group. So this is the stellar mass of the host. And these are the constraints from observed dwarf galaxies, low mass galaxies. And this is the occupation fraction. And these 4 panels are once again the models with just seeding, those semi-empirical models that I showed you predictions from them. Those are the blue boxes. So it would be fair to say that at the moment, we are kind of tilted. The evidence, the observational evidence is tilted, and heavy seed models are not ruled out. At least that's what I would say. Although, I can probably be a little more bolshy and say they are very well supported by the organization, by the way low mass galaxies are organized at low redshift. So, I would argue that there is growing evidence in support of heavy seeding models. So let me now get back to our favored DCBH model. And I think one of the interesting things about this model is that you predict the formation of these red collapse seeds, you predict this transient population of overmassive black hole galaxies, and then you know that over cosmic time, when you build these evolutionary models, galaxies have to end up the way we see them today at redshift 0, where the stellar component dominates in mass over the mass of the black hole hugely, right? So the mass of the black hole is only a small fraction, 10 to the minus 3-ish, of the mass of stars today. So what this allows you, so this is the theorist's favorite model space that's open, right? So we can come up with the various trajectories, various ways in which you essentially invert what you're seeing transiently at high redshift. So this is a very nice rendition that my former student Angelo Riccardi, who built those models, is showing you for heavy seeds. So this is, you see a redshift, the clock evolving. These are the data seen at redshift 0. This is the local M sigma relation. And this is the various journeys of various seeding mechanisms, various accretion processes. So I'm just showing you one snapshot from the kinds of models that we produced. And you can see already that, in terms of where heavy seeds start out, they start out well above the local relation, and they slowly move towards. So this is just one outcome of this Monte Carlo process that involves tracking the merger of halos in CDM, populating them with black holes, and growing them. So the transient overmassive black hole galaxies will depart from local scaling relations because A, we are seeing them close to the seeding epoch. As we just saw, they start life out overmassive. But they will not remain off the scaling relations for too long from the seeding alone. There could be other processes that actually cause them to deviate from scaling relations. And we'll come back to that. So coming back to how we actually predict the observational signatures, as I responded to Elliot's earlier question, it's a very simple setup. So we start with the seed. We look at the merged stellar population from the POP3 parent host and the DCBH that has formed in the subhalo. And then we evolve that combination using a 1D hydrodynamical code. The stellar population is evolved separately, and the black hole is grown. Super Eddington accretion episodes are allowed, and then we actually merge them to produce the output spectra in post-processing. So this is the predicted spectrum over the range of relevance for JWST. So these are the observational limits, the black that you see. So anything, any signal that booms over that is going to be detectable. Once again, the cool colors and the warm colors here actually now refer to different metallicities for the assumed metallicities for the stellar population. So remember, we have some freedom with the population, the stellar population, depending on which window we actually form them. So here you have a growing heavy seed with the stellar population from the parent that is somewhat enriched. And then you have one where you have zero enrichment. And again, this is the combined spectrum of the accreting black hole and the stellar population. So these are other confounding spectra, like extremely dusty ellipticals and so on. What is interesting is there's a very clear-cut signature for these sources. There's a sharp change in flux between 1 and 2 microns. So they really stand out. They should be detectable, very easily detectable with JWST, right? Remember, however, one of the key discriminating features of these OBGs is that they have to be X-ray bright. So the scenario cannot be tested unless you have the X-ray flux. So the X-ray flux has to actually dominate, comparable or dominate the infrared flux. So this in turn is the prediction, the spectral prediction for the POP3 seed. And we believe this is going to be mostly undetectable, maybe very marginally so. Oh, by the way, I should point out all these lines, these recombination, are just hydrogen-helium recombination lines. So we just did not do super sophisticated additional lines because it's pristine gas, right? So this is pretty pristine gas. And this was done with cloudy. So I should give the shout out to Gary Ferland here. So these, you will see that a population 3 seed, a light seed by the same epoch would just be very marginally detectable with JWST. So anyway, this was the prediction. So let me now tell you a little bit about the data that we have in hand. So one of the most remarkable gifts from nature are these gravitational lenses that are provided by vast aggregates of dark matter, particularly associated with clusters of galaxies and galaxies. In this particular case, we are looking at massive clusters of galaxies that act as some of the most dramatic magnifying lenses. And so this is a cluster from the Hubble Frontier Field Survey project, which also initiative that I had the really good fortune of being involved with and modeled all 6 of these clusters that were so very, very deep look with Hubble. And these are the various teams using different independent algorithms that calibrated the lenses. So this is the high magnification region in the inner parts of these clusters. These are very well calibrated. And as you can imagine, to exploit, so you can look through regions of these highly magnified clusters, and you would preferentially, therefore, be able to find very faint populations of galaxies and in this case, galaxies and AGN, that you are unlikely to ever reach even with the deepest look with JWST. So we leveraged the maps that were made with Hubble, and there were JWST programs that looked through these clusters to detect the highest redshift sources, highest redshift galaxies. And we've had a fantastic haul. And I just want to shout out here to several additional clusters other than Abell 2744 that are now going to be used to uncover these. And boy, did we have good luck. So we ended up getting two sources, UHZ1 and GHZ9, behind Abell 2744. So these are background, extremely high redshift greater than 10 sources that were magnified by a factor of 3.8 and 1.5 respectively. UHZ1 is more strongly magnified than GHZ9, that bring it into view for JWST. And therefore then Akush Bogdan at the SAO reached out to me just before, after our paper came out with the predictions, that we should propose for a deep X-ray look through Abell 2744 to follow up, to look for OBGs if they're there. And we got super lucky. So we definitely found one, and that is UHZ1, and a very strong candidate, which is GHZ9. So here are sort of the properties. GHZ9 is at a redshift of about 10.8. This was a photometric redshift. I gather recently there's a confirmation that this is indeed at the high redshift, extremely high redshift of the 10.5 plus. And this has, from the JWST data, the black hole mass is estimated to be in excess of 10 to the 7 solar masses, so well supermassive at this point. And this is lensed and magnified by Abell 2744 by a factor of 1.2 or so. As I told you, we have incredibly well-calibrated mass models. The X-ray detection in our program was at the 3.5 to 4 sigma for GHZ9. GNZ11, as you all know, is this extremely distant galaxy. It's not in the Abell 2744 field. This is a source that has been very intriguing for a very long time, redshift 10.6, and has a black hole of 10 to the 6 solar mass, so another supermassive black hole. And now this is the star of the show, UHZ1 at a redshift of 10.1 with a black hole mass of 10 to the 7-ish and a 5 sigma now detection in the X-ray. So when we published the paper last year, we were at 4.6 sigma. We didn't have the full survey data yet. We had 85% of the data. And now we have the full data, and it's 5 sigma. So this one is luckily for us. So you can imagine so many strokes of luck. So magnified by a factor of 3.8, that really brought it into view. So then you can do the simplest possible thing and say, okay, let's look at let's look back and predict some simple trajectories for growing from seed to the mass at redshift 10-ish for these sources. So if you look at UHZ1 from heavy seeds, it's pretty straightforward. You can just be Eddington limited, and you would very comfortably reach that value of measured mass. Whereas if you start with a light seed, then you would need very handcrafted, either steady super Eddington accretion or very, very baroquely tuned episodes, short-lived episodes to get you there. And remember, I already told you that simulations are telling us that the environments that you find POP3 light seeds forming in, they are not the most conducive for early growth, unless they happen to, be in the vicinity of a giant molecular gas-rich cloud, in which case, yes, they can grow very dramatically with a steady super Eddington rate. Otherwise, these just don't grow, just to tell you that that's where we are at. So so it's very clear that you can comfortably start even at Eddington limited rates and reach this match for UHZ1. But remember, the evidence as such for making a case for heavy seeds is not just this simple growth model. It's the entire multi-wavelength prediction of those for these OBGs that I just discussed. So just to kind of bring it all together to show you what the contrast is between seeding and how we are trying to constrain seeding at these early epochs, So we started out, we modeled for UHZ1, starting out with a light seed. And that's, 10.1 is about 470 million years after the Big Bang. So we predicted what that spectrum should look like. And we start with a heavy seed. As at very early, let's say the seed forms at 2025, it doesn't really matter where you form it. Then by 12 to 9, you have to be detected. And UHZ1, I'll show you in a minute, looks like the first very credible OBG candidate because it satisfies all 6 properties that we predicted for that particular scenario. And so this is just to show you, this is the X-ray data over the JWST. That's the NIRCam zoom on UHZ1. Obviously, as you all know, it looks pretty unpresupposing as a little blob. But the question is that there was a Chandra detection. And this was a 2.1 megasecond observation in this field. So, I mean, it's really astounding, like 24 days of staring, right? So the evolutionary consequences out to late times and the journey on M sigma is something that we are actively working on, but we were able to show that the properties of UHZ1 are really consistent with those predicted for OBGs from direct collapse. So I just want to point out that, overmassive black holes that lie above the local relation, right, are being seen all the time now at various epochs. So you have to be, it may not be a signature of early initial seeding, because it depends on the epoch. As I told you, as you move further and further away from the seeding epoch, there are many other astrophysical processes that come into play, in particular feeding and feedback, and the relationship between feeding and feedback in galaxies. So we also know that at very low redshift, we have overmassive black holes, for example, in Leo 1, in the satellites of the Milky Way, where they've been found. And remember there, the reason they are overmassive is not necessarily seeding, but it's because of the particular dynamical environment they are in, right? So they have been tidally stripped, because these are satellites, they've been tidally stripped. And so the black hole is actually overmassive compared to the stellar component. You've lost a lot of the stellar component falling in. So let me take you to, so I do want to mention that a lot of the early work that I did was with my postdoc then, Giuseppe Lodato, developing the sort of direct collapse scenario and the formation of OBGs. Okay, so this is the computed spectrum, and I've removed a lot of the other sort of busy things that I had earlier on. And I'm just showing you the NIRCam MIRI bands, the spectrum for OBGs where the stellar component, the metallicity of the stellar component is 0 metallicity, 10 to the minus 3. And so I just want to give a shout out here to the fact that there have been many other groups that are working in other scenarios, including other ingredients, and making predictions for JWST spectra. The reason I'm focusing on OBGs is because there's a direct line from theoretical understanding to observational predictions, and we have found something that satisfies all the predictions, right? So, but I do want to mention here that there's a very active group in Paris led by Mata Voluntari. There's a group in Rome led by Raffaella Schneider and collaborators. And there are these simulations that are being done. People are trying to sort of bridge this gap of what we can do with black hole growth. So let me show you all the predictions that UHZ1 satisfies. So this is the full multi-wavelength prediction for OBGs. So you expect an elevated infrared flux, and you have appreciable X-ray flux, but a lot of the X-ray has been reprocessed into the infrared. And then in this sort of color diagram, you have to be in the X-ray dominated phase, as I mentioned. So that is really where UHZ1 is. And this is showing you that there are no sources. We looked really carefully to find other OBG candidates in either CANDLES or Good South. We don't actually see anything yet. There are no OBG candidates. They should all be above in that region. And this then is the spectrum that we modeled and predicted. Our model prediction, so we generated a library because there are many parameters here. We generated a full library of spectra. And this is the spectrum. The data is in the blue points with the arrow bars. And it's really quite remarkable. I think to have all these pieces fit simultaneously, that's the X-ray detected, measured X-ray flux, measured infrared, and this spectrum that tracks, as well as the fact that you can actually make it, it all hangs together, providing, I think, compelling evidence for direct collapse black holes. Okay, to start wrapping up, I'm often asked, right? So how do we discriminate? You could have, of course, there's the proverbial, well, you could have had super Eddington accretion for short periods of time and grown it. As I've told you, we don't actually see those environments in our simulations. We don't find these light seeds in those environments. But that aside, you may ask, okay, what is the redshift range? Is there a sweet spot in redshift where if you detect a source, you can clearly discriminate, right? Obviously, as you go further back in time, if you find a source between redshift 16 or redshift 14, then you might be able to say something about whether the growth on average has been dominated by super Eddington episodes or has been Eddington limited, and therefore say something about conclusive about seeding. And I just want to then quickly see if, how many more minutes do I have? 5-ish. Okay, I mean, I may have to skip a couple of slides, but so I just want to point out here that for black holes, right, it's been really very rich to combine data sets of populations, so luminosity functions and mass functions as a function of cosmic time with individual objects, these outliers at very high redshift. But as I said, there's a complex, the problem when you see a black hole population at low redshift, for example, all of these physical processes have come into play. And so what we really want ultimately to build these semi-empirical models to be more realistic is you want to know the accretion rate and the environment of the characteristic black hole, not the extreme mass outlier at any epoch. That is very, very challenging. So I want to give a plug to some work that we've started. We've been assembling a database, a unique database in which we co-locate both observational data, of course, taken from SDSS primarily and many other surveys for black holes above redshift 3. So it's a project that's really focused on high redshift black holes. And then we simultaneously store slices from simulations at similar epochs with box sizes, whatever is available. So we co-locate these simulation slices with the data that allows certain kinds of abundance matching and lots of interesting analysis and predictions that can be done, leveraging, of course, machine learning. The way in which we leverage machine learning, as you all know, the volumes of simulations are completely incommensurate with the survey volumes at the moment, right? SDSS is like 1/3 of the sky, right? So we have quasars from 1/3 of the sky. And in order to start building up simulation volumes, as you know, including all the baryonic physics, et cetera, is completely intractable to produce a simulation with a volume that is comparable to the 1/3 of the night sky, right, to make predictions. So what we did was we started with illustrious TNG 300, which has a version of feedback processes, star formation, black hole growth, everything cooked in. And as you all know, dark matter only simulations are super cheap to run. So you run them and you first train on illustrious TNG, start with a small box of dark matter only simulations, populate the black holes, the quasars from legacy, trained on illustrious, and then we start expanding the box. We start making bigger and bigger boxes. And so this is a project in which we use the legacy simulation and have run bigger and bigger boxes. And then we populate quasars into those large boxes. Right? And then you can make comparisons with the data. So I'll just quickly tell you why this is interesting. So here is a wonderful paper written by Melanie Habuzit from a few years ago, where she compared the predictions for the population of redshift quasars. The known quasars are shown here in green. And these are 6 of the sort of state-of-the-art simulations. And I just want to alert you that almost none of the simulations actually reproduces this population at redshift 6. And these simulations all have various different prescriptions for star formation, feedback, and so on and so forth. So that's the current state of play. Okay, so we really are not producing the observed population. So part of what motivated our work was to start looking at lower redshift, and we found that even at low redshift, we don't actually reproduce the properties of Sloan quasars. So I just want to give one quick shout out before I put up my conclusions, and this is to some very new, interesting work led by Hei-Rin Cho, who is a graduate student of Ramesh Narayan's. And we've been working with her on a very ambitious project that many people at Princeton, Elliot, Jim, and others are also pursuing, which is to try to bridge this gap in understanding black hole accretion from horizon scale GR-MHD simulations, coupling them to cosmological simulations. Ultimately, the flows of gas have to come from large regions, kiloparsecs, megaparsecs even. They have to make it all the way down to parsecs, subparsecs, right? And so there's a complete disconnect in the community and in the astrophysics. And it's not because people haven't thought of it before. It's just numerically really difficult. So this is a project we've started doing to bridge these scales, because this will give us better recipes for. So one of the things that is done in all the simulations is that when a gas particle crosses the Bondi radius, remember Bondi radius is well outside the horizon, it is assumed to be accreted in these cosmological models. And so when you couple, and in the first set of simulations, we found that only 1% of the gas that crosses the Bondi radius actually makes it to the horizon. That has huge implications for the kinds of recipes and models that people are putting into cosmological simulations. So just want to show the state of play is complex at the moment with JWST AGN from redshift 6 out to the highest outliers. And one cute way to maybe find black hole seeds, to constrain black hole seeds, and also pop 3 stars in one go, killing two birds, killing the one bird with 2 different stones, is actually looking at POP3 TDEs. So POP3 stars disrupted by UHZ1 type supermassive black holes that are already in place at redshift 10 or so. And it looks feasible with Roman, not with JWST. The field of view is too small to actually detect those. So I'll just stop here and put up my conclusions. Thank you, and I'd love to have questions.
Questions for Priya?
Hi. So wonderful talk. Thank you. I was going to ask more about UHZ1. You were stressing just how lucky we were with the, having the deep X-ray exposure where we have the magnification and anything. Can you say anything about predicted number densities of such objects? I mean, observationally, we have statistics of 1, and I guess the question is just how lucky were we? Or are these ubiquitous if we could find similar?
Great question. We don't actually know. It's a very tricky calculation. What we do know is that if POP3 seeds do lead, that's the legitimate seeding mechanism, that mode is likely to dominate. However, so compared to POP3 seeds, if we assume somehow, remember the uncertainty is there with the initial mass function. So if we somehow assume that the mass function of the first stars is tilted quite high, you start out with an advantage, as much of an advantage as you can with their birth masses, and that somehow we are missing in the simulations how they actually grow. We're missing a process, as I told you. At the moment, it doesn't look like they can grow that fast. It looks like because we see so many stars that need to have formed from the recycling of multiple episodes of star formation, that would be a more efficient process if we can close the loop on the entire mass growth. So I think the only thing we can say is that we do not expect this to be a super efficient, this particular DCB, because UHZ1 only ratifies the direct collapse and the formation of the OBG. Remember, there are many other kind of massive seed formation channels. So we don't think it is super duper efficient as the channel for POP3. And we also know, we know this from simulations already, that a black hole that is the most massive one, we know this from simulations, most massive one, the brightest quasar in the box at 10, is not the brightest quasar in the box by the time you get to 6. Because what matters is not just the halo mass and the galaxy mass, but the environment, the details of the environment, right? So I think it would be fair to say, therefore, that all the redshift 6 and 7, a small fraction of the redshift 6 and 7 quasars that we see likely descended from DCBH. I think that's as far as I can go. So they are not going to be as abundant as this particular channel. Once again, if it turns out that all the massive seed channels really are feasible and we find sources that ratify each of those channels, then it may well be that massive seeds might dominate. Massive seed channels all put together might be the dominant source. This one particular channel, it's pretty hard to extrapolate.
Priya, at least one of your early scenarios for the drag collapse involved this pristine gas which is unable to cool and forms a disk. I presume because there is a lot of angular momentum, these asymmetric inflows. But then what happens, how does this rotating non-cooling object actually evolve? Do you have a gravitoturbulent disk that feeds some central...
central object that is forming, once again, this has not been numerically tracked. Pardon?
And in this case, you form just one black hole.
Yes. So I think, that's what we have claimed. This has not been numerically followed up quite. And it is possible that you could fragment. I don't know, open question. Yeah. I think it'll be very interesting. I think part of the problem has been that the simulators have wanted to start from the initial conditions and follow the story to see how far they can go. Maybe the tactic we should all change to is say, okay, let's start as a given that you have this very massive disk that has gone highly unstable, and then follow up to see just from there. Let's not worry about how you got there, but say you're there, and then see how you evolve. And those simulations are not quite there yet. People have started doing, again, they're sort of, quasi numerical models. So Mitch Bagelman and others have made the case that you form maybe an object that looks like a quasi star. It's sort of not a star, but not quite. It has like a, an envelope like a red giant and so on.
But in this case, the collapse will not be direct in the sense that it's happening on a dynamic level.
Exactly. So so I think that, so I think we've not really, that's an open question, and definitely now worthy of following up. Because it's credible. As I told you, even 10 years ago, I used to be giving talks about massive seeds, and people thought, it's hand waving, it's not interesting, and it's not going to be viable at all. So I think now there's enormous renewed interest in seeding. I mean, seeding is a thing. There wasn't even a question about whether this was a big open question about seeds. People thought everything was locked away with just population 3 light seeds.
We can take our last question from.
Are you at all inclined to consider the possibility of primeval black holes?
Yes. Oh, I forgot to mention that. Oh, totally open. The problem there is finding a unique observational signatures. Is, as you all know, once matter has fallen into a black hole, there is no way of knowing how it, what's inside, how it got there. Obviously, the information should be held within the environment, within the host galaxy. So one of the interesting things, as you all know, the resurgence of primordial black holes started with these LIGO events involving 30 solar mass stars that you couldn't make in one step, and you would need kind of multiple steps, right? And they proposed that maybe those are all primordial black holes. So, and they realized immediately, right, that how to link these black holes to their hosts was tricky. So the obvious thing was to say, well, maybe all the dark matter is made of primordial black holes, because then that gets completely rid of the problem of how do you populate the PVH that has nothing to do with dark matter in a dark matter halo. Do you do 1 in every 10? How do you do it, right? How do you actually do the population statistics? That was not. So now it turns out that PVHs are not a credible dark matter candidate. They definitely cannot explain the majority of dark matter, maybe a small fraction. And the window is getting, tighter and more broke. So then we are now left with the problem. And this is something that a couple of my students have been thinking about, how to, in a lambda CDM universe, where primordial black holes have nothing to do with the dark matter, but they do inevitably form in the early universe. Looks like they could inevitably form. in the extremely early universe. There's a very nice paper that showed that, QCD phase transition, you could get a population of primordial black holes, right? So we don't yet, we're trying to still figure out that if you have this population that is in place during the radiation dominated era, then radiation matter equality and transition, how they actually grow, what their masses are going to be like by redshift of 30, right? So that's sort of, what is the starting point? And there's a lot of freedom in how we populate them. And depending on how we populate them, we may be able to match mass functions and luminosity functions. So I think the word is open on that. I'm completely open to the possibility that we could have a population of primordial black holes in the mix. But I think what is clear that not all the supermassive black holes that we see today could have descended necessarily from PBHs. It's not clear because you would have to really tailor the abundance. And there's just too much freedom there at the moment. So I think I'm completely open. Yeah, I should have put on the slide. And so we worked a lot on the other problem within the context of accounting for dark matter and simultaneously accounting for seeds. And I just want to point out, I think Phil Hopkins is visiting you, and I think he's also worked on those kinds of models. We're trying to account for early black hole seeds from primordial black holes.
Let's thank the speaker.